So, let us keep one practical example in mind. The practical example that you should perhaps concentrate is on a case where you enter a departmental store like Walmart, large warehouses, large wholesale shops like Walmarts or big bazaars that we know very well, which are split over several floors, and you are interested in sort of a mechanism where at the end of the day a robotic platform equipped with all the necessary infrastructure for reading tags is made available, and this robotic platform walks across several narrow corridors from rack to rack. There is a narrow corridor, is not it? It uses that corridor space, scans on one side for all the items, comes back, scans on all the items on the other side, and sort of localizes that particular section of the floor area. Okay. And it does this for all sections of the large departmental store. So, let us keep that as the goal you want to do. Okay. But obviously for us to demonstrate all this is not going to work. We will see if we can show you a very small part of this course, whether we can cover that little demonstration using all the principles that we have learned for RFID based localization. Again, it is still not complete in terms of our discussion unless we see one paper or one literature work which sort of summarizes all this into a possible implementation of a system. Let me point you to a paper that which is quite recently published, and this paper is on anchor free backscatter positioning for RFID tags with very high or high accuracy. Look at the portions where our project staff have actually marked the things that you will really have to drive home when you read this paper. First thing is this paper dismisses the same problem that we discussed a while ago. RSS based methods are vulnerable, you cannot do anything with respect to distance and tag orientation. So, let us put that out of the picture. AOA methods put a strict constraint on number of antennas in terms of antenna spacing that readers directional antennas are too large to meet. Okay, so, this is essentially what we have also described with respect to the different localization methods that are applied in RFID, and so essentially they are all using angle of arrival based methods only, where there are multiple receiver antennas. So, here again it is again focusing back on phase, which is indeed a stable indicator highly related to tags position and preserved over frequency or tag orientation, but challenged by its periodicity and tags diversity. So, essentially it is trying to say let us go and explore phase to the maximum possible extent to see if you can localize these tags, okay, by keeping a few constraints in mind. Again you recall the antenna spacing that we discussed in detail. Here again it is talking about this antenna spacing should be less than lambda by 2, and the idea is back that if you want to infer distance difference lambda delta d from a target tag to 2 antennas using phase difference method delta theta, you must have this lambda by 2 constraint applied in this applied to this. So, that means A, the term A that we remember very well is should be less than lambda by 2. In this situation the delta d can be determinately formalized as a piecewise equation with parameter delta theta, right. Then the hyperbolic positioning is employed to locate the target tag. So, let us see how this hyperbola can be drawn using one delta d on which the points are candidate positions of a target tag. Okay. When you draw hyperbolas, you read a tag, you are exactly not talking about one single hyperbola, but several hyperbolas which are sort of ideally expected to intersect at one point. Once that all these hyperbolas intersect at one point, that point indeed is the actual xy location of the tag. But far from reality, this is never going to happen, because when you read, you will form hyperbolas which are all never going to intersect at one point. So, you have to find a method to sort of localize them. In other words, to narrow the uncertainty, you will need not only need multiple hyperbolas, but you will also need a good way to arrive at what is the what would have been a actual intersection of all these hyperbolas. In other words, as we discover, we will see that you need a clustering algorithm as well. At the moment, it may sound a little unclear about how all this is to be done, but I am sure as we read this paper, you will see clarity emerging from its practical application in order to do localization. Now, this is all basics, so let us skip all of this, but do keep in mind that many issues, many parameters are associated with the actual phase that you read, which includes the reader's transmit circuits, the tag's reflection characteristics, the reader's receiver circuits, and so many other issues. So, essentially there are terms such as theta t, theta tag, theta r, all these are contributing to the actual phase that a reader antenna actually obtains. So, all of this will have to be expressed in some form, and you can see that this indeed is the simplest way that one can represent. Let us look at this expression theta plus 2k pi. This is the phase that you get, that actually this is the phase you should get between the tag and the reader, okay. That is the left hand side. The right hand side simply says this phase is corrupted, is manipulated due to several impairments, right, which is simple. That is let us look at that. Theta t, theta r and theta tag are all the impairments that will get added when you are measuring this actual phase 2 pi 2d by lambda, okay. Now, if you take 1 and you take 1.1, supposing you take 1.1, 1.1 is another phase for another distance, right. You know, you take another, you take it to another, take the reader to another position, you get back the same expression, right, which is in another position, that is why we did 1.1, and you do a phase difference. Now, substitute for this, you substitute as theta 1, the other for the other separation you substitute it as theta 2, then you do theta 1 minus theta 2. It is clear that this part of the expression becomes 0, it gets cancelled out. So, you are only, so in other words, the point that you have to note is that theta t, theta r and theta tag are easy to eliminate if you do phase difference method. This is the basic underlying principle under which this can be in other way calibrated out, as they say. You just calibrate it out by simply cancelling out these terms. Also observe the interval over which theta is falling, okay. This is very important. The interval is not is not a completely closed interval. You can see it is closed on the left side, but because of the distance that the tag and antenna, the reader are situated, the right side is not a closed interval, right. There can be n rotations after which you can read theta, and therefore this is not really a closed interval. Recall I mentioned about equation 1 and equation 2, right. So, equation 1 is this, right, you can see here, and I said let us put this as theta 1 and then let us put the other one as theta 2 and do a phase difference, and let us estimate the path difference and all that. This paper actually has captured all of that, and you will get a clearer picture as you look here. You see exactly equations 2 and 3 are that. You can see here he assumes one position, antenna position, gets you the same expression theta 1 plus 2 k 1 pi is equal to 2 pi 2 d 1 by lambda plus all these impairments that are associated with phase, and similarly theta 2. Now you subtract two of them and you simplify, you will get this delta d is equal to lambda by 4 pi delta theta plus 2 k pi. In other words, a beautiful relation between the path difference and the phase difference. Essentially that is what RFID localization is all about. If you are using hyperbola based positioning, you find out the you do a phase difference and then you find out the path difference, very very important. Now suppose the delta t is able to be inferred from delta theta, can we reveal the actual tag position? That is the beauty. The answer is yes, and as you know, you can apply well known hyperbola, and this is nothing but a curve that is composed of locus points for which the difference of the distances from two given fixed points is a constant, and once you know delta d, we can construct such a hyperbola that focuses on two antenna positions, and you can nicely formalize this as this simple expression which is delta d. X and y are the tags location, x1 y1 is the first position of the antenna, x2 y2 is the second position of the antenna. From there you will be able to estimate this delta d. Now the hyperbola equation is quite simple. You can see x square by a square minus y square by b square. A square a essentially is delta d, b is square root of c square minus a square, and c you can easily get by this simple Euclidean method, which this divide by 2 is essentially saying that the hyperbola is forming in between the two reader positions. Okay, the two in between reader positions, or I would say antenna positions, and that is easy to infer. Let me just pull out this thing here and concentrate on this picture. Supposing you did one reading from 0 comma 0 and the other reading you did from 0 comma some 8. When I say 8, I mean some centimeter, it can be some units of centimeters. That means I moved 8 centimeters and made 2 readings, or I had 2 antenna, one at 0 0 and one at 0 8, and I was throwing power at a tag which is located at xy. This is x1 y1 and this is x2 y2. The hyperbola is essentially formed in between the two, right. So at 0 comma 4 you can actually draw a nice hyperbola, right. If you look at this this little chart that I have here, it is actually capturing all that we discussed. First step, you need to have successive antenna positions which are separated by lambda by 2. You calculate the phase difference between successive antenna positions. You arrive at lambda d is equal to lambda by 4 pi delta theta plus 2 k pi. Then you have hyperbola formations. Then you will have multiple intersection points. The question is, how do you actually estimate the actual xy of the tag if you have so many intersecting points? As I mentioned, one simple way is to try and use a clustering algorithm, and so one such clustering algorithm is indeed the DB scan. DB scan is a very popular clustering algorithm, and we can go back and look at how this DB scan works in a few moments. But before that, let us see if there is any further discussion. So this divide by 2 essentially is coming because of the fact that the hyperbola is formed in the middle, exactly in the middle between the two antenna separation points. Just look at this picture which is sort of capturing several parts of the RFID hyperbola positioning. Let us assume that the reader's antennas can be positioned in A1, A2, A3, A4, A5 and so on, many positions of the reader antenna are possible. And so if you look at the hyperbola that form between A1 and A2, you can see between A1 and A2 T1 C1 hyperbola and C3 hyperbola are available, right, are intersecting between A1 and not intersecting, they are available between A1 and A2, are formed between A1 and A2. If you look at A2 to A3, you will see that C2 and C4 are being formed between the two of them. Now you can go on like this, right. So so you go to the next A4 position and so on and so forth, and then you realize that the tag itself can be anywhere in these positions, can either be in T1, can be in T2 or can be in T3. As a result, if you want to reduce this error in estimation of where it is, one simple way is you divide A1 A2 that the distance again into by half and have one more position, let us say A1 prime, let us say something like A1 prime here, and here you have A2 prime, and then again form two hyperbola there, and then look at the intersection of these hyperbola. Then you will actually come to know which is the actual position of the tag. So now we did this hyperbola formation between two antenna positions and intersection of several hyperbola happening, and then you are interested in knowing the actual xy location of the xy location of the tag. We did some measurement and I just wanted to show you, point you back to where exactly the problem is. Look at this picture. This is some position, 1D position, which I am interested. This has some xy location in reality, okay, and that would be easy if all these hyperbolas which are going are all intersecting. I just taken a sort of a line segment of a simplified line segment of a hyperbola, and I have just shown you where exactly the intersection is happening. That is happening here quite well. This is what should be happening, but that is not really the case. Look at how these line segments from different hyperbola are actually intersecting. You will see that they are all at different points, and you have to infer somewhere xy that is available from these points, right. So this is not going to be easy, and it has been found that DB scan, you have to do some form of clustering, and it is found that DB scan is a good way to cluster them. It is basically quite simple, it is a density based scan, and essentially it is a spatial clustering which is used from all the hyperbolas that are formed. So you group together points with many nearby region and eliminate all other points which are considered as noise, and use to form, basically this is used to form multiple customized clusters, and straightforward densest and the closely packed cluster is taken into consideration. If you look at this picture, this definitely is not part of any of the other clusters, it appears to be an outlier, so actually you can eliminate them. Similarly, you look at this C and look at this B, they are part of the cluster, it is not that there is no intersection or anything, but they appear to be far away from any dense point. So they can also be eliminated, and the tag position indeed is within this color that you see here, quite dense. So this is the exact idea behind the density based scan. Alright, how do you do this? Let us run through a few steps which will allow you to actually implement this DB scan. First of all, if you look at this picture, there is a certain radius of this each circle here. So you need to define what should be your radius. If you have a large radius, all these circles will vanish and become a very large circle, right. A slightly larger radius will also encompass N, B, A and C. So, you do not want to do that. At the same time, you do not want very small circles such that only 1 or 2 hyperbola are sitting inside them, okay, just this one simple circle is sitting. So, you want some sort of a via media or a nice compromised I would say network diameter or circle radius which will allow you to group all these hyperbola intersections, right. So, this epsilon and indeed is the radius, you can say it is equivalent of the radius, and number of points which are sitting inside them essentially will tell you whether this should form a circle or not at all in the first place, whether it should be part of a circle or not. Look at this epsilon, maximum radius of the neighborhood of any point, any point, and minimum points, minimum number of points to be not considered as outlier. So, which means again look back at this is indeed an outlier, right. So, you need some points, minimum number of points to be declared to be part of a nice cluster, and only then you can say something about it. A point P is a core point if at least minimum points are, this is indeed like a variable. So, minimum points are within the distance epsilon of it. These points are said to be directly reachable from this point P. Okay. So, point Q is reachable from P if there is a path which consists only of core points from P to Q. Look at this picture again, you can see these arrows are indicative of that, right. These arrows are indicative of this point Q is reachable from point P if there is a path which consists only of core points from P to Q. The core points and reachable points form a nice form of sort of cluster. So, I will go back and then I will show you. You can see that within this nice nice circle here, there are P and Q which are within them and they form a nice beautiful cluster. This is one cluster, there can be another overlapping cluster here, there can be another overlapping cluster, because as long as these definitions are adhered, you can actually call them nice clusters. All points not reachable from any other point are essentially outliers. Again this becomes an outlier, as you can see. In other words, this is easy to implement, okay. So, and you could actually try, we will provide you some data files, we will give you some traces of what we have from the experiment that we are going to show you, and that trace you can use, and you can use any programming tool of your choice. You can try MATLAB, you can try Python or whatever, and try and find out the actual positions of the tags. This is like an exercise which you can implement and try, okay. So, you will have to implement these algorithm, this algorithm implementation you will have to take up. Data for trying is something that we will make available to you. So, welcome to RFID demonstration. You might have already seen that there are 3 ways by which you can do phase difference of arrival based localization, and specifically let us look at the spatial domain based system, phase difference of arrival based mechanism, and let us just look at how we do that. The big picture is very simple. This is a departmental store, right, and then it is a supermarket. There are a lot of items kept inside a rack, and you are interested in localizing each one of these items. So, the problem statement is very simple. There is a rack on the left side and then there is a rack on the right side. Okay. The left side of the rack essentially has 2 items here which are both tagged. Okay. You can see that there is a left side, extreme left, there is a tag on top, you can see the orientation, it is almost vertical, and then there is a number there minus 120 80, this indeed is the ground truth. Okay. Then come to this, this is placed at some 45 degrees, you can see a tag on top, and then this one's ground truth is minus 60 comma 80, and this is the corridor in which you are going from rack to rack. Here is another tag placed on top, its position ground truth is 60 comma 80, and the other one is 120 comma 80, some units you can call it centimeters, right. So, the big picture is that you want to localize them. Okay. Now, how do you do that? So, one idea that you can explore is you have a single antenna system here, and supposing you make this antenna move spatially from one location to another location, you do phase readings and then take the difference of them, you must be able to convert the phase difference to path difference and therefore be able to localize based on the expressions that we saw in the class. So, let us see what exactly we plan to do here. Thing is, there is a reader here, this reader is from a company called ThinkMagic, and it has a beam width of 65 degrees. You can have antenna with different beam widths, you can have antenna with different gain. This antenna appears to have a gain of about 8.5 dB, and you can have higher gain antenna as well, right. So, this is the antenna that we have chosen here, and it is throwing power at plus 18 dBm through all these tags. If you put more power, if you throw more power, reflections from all these sides will come. They may even power the right side and start reading from this location. So, you have to choose transmission power such that there are not too many reflections coming from all across the departmental store, sort of, yet sufficient power so that these tags will be able to read. Of course, there is a challenge of tag orientation. If the tag orientation is proper, then it will read, otherwise there can be issues there, but we will keep that out of the mind. The reader essentially operates in India, RFID frequencies are typically from 865 to 867 megahertz. There are 4 channels and there is no control on which channel the system is actually choosing, it actually hops across these 4 channels. So, we will have to assume that at some f that it is reading these tags. In fact, it could be reading one tag at 1f and it could be reading at f1, let us say, and it could be reading the other tag at f2, but all across this narrow 2 megahertz range over which the RFID transmissions are permitted in this country. The reader actually communicates to the tag using FM0 encoding, okay, and also there are additional settings which the reader should be able to do, which includes setting it to single target, session 1 and so on, right. So, all of these settings essentially are specific to RFID reader, and those settings are all compiled into a nice beautiful Java code developed over the years by our project staff from our lab. Ending with Ms. Tejaswini and Sanmay Patel really working on trying to improve this code both in terms of writing newer functions and also improving the localization accuracy. Okay, so that's one part. Then there is also the requirement that the Kubuki, the robotic platform has to move, right. All of these functionality essentially means that you need one nice Java code which will also take care of moving the robotic platform from one position to another spatial position, so that you will be able to read the phases from both these positions. So, the distance that it moves is less than lambda by 2 is actually 8 centimeter, which is much less than lambda by 2, right. So, that is the point. So, all of this is so essentially the script that is running on this computer, which is essentially a Raspberry Pi, essentially has the ability to move the robotic platform by 8 centimeter and also has the ability to tilt the reader to about 16 degrees, so that the tags are read successfully as much as possible, improve the probability of successful reading by tilting it to a certain degree. So, this is one part of the experiment. After all of that, the tags are read, the phase difference of arrival is considered, put into hyperbola expressions, and ultimately you want to print the localization, the algorithm has to print some numbers, which in our hope is that should match this ground reality numbers. So, let us start the experiment and see how we will be able to start localizing. So, now let us start and let us focus on movement of the antenna. So, a command is issued, the antenna, the robotic platform is all set, a command is issued, the starting location of the robotic platform is at 0, 0, that is x is 0, y is 0, this is the reference position of the system and it starts to move from there. So, it makes one reading there, goes to the next location, makes waits there for 10 seconds, makes one reading there and proceeds like this to about 11 positions, okay, before it stops at 0, 80, which is essentially the resting position for just one part of the rack. Then you start with the second part and then it reads the second part. Okay. So, let us do this basic demo. So, you can see now that the reader antenna has shifted to some angle which is roughly 16 degrees and then it is trying to read a set of tags and now it moves. You can see it is moving 8 centimeter, very small movement, waits there for 10 seconds, makes a reading, hopefully reads these tags with a high success probability, gets the phase information, goes to the next reader location, reads the tags here and then in this location and then makes the next movement to another location and therefore, successfully gets phase readings one after the other. Essentially, you should be able to start creating hyperbola, start forming hyperbolas. In this case, a hyperbola is typically formed here. This is a hyperbola. Okay. So, here exactly in the middle between 0, 0 and 0, 8, at 0, 4 the hyperbola is formed. And once these hyperbolas starts intersecting, you realize that the intersection point indeed is the actual location of the tag. So, you have to solve the hyperbola equations and therefore, and arrive at the decision. So, what is the at each position antenna position what exactly is being read is also important, right. So, you can see that you get tag ID, okay, the protocol which is EPC Gen 2, this is the tag ID which is here. It has to read the phase, otherwise how will you do phase difference. So, it is reading the phase, it is reading the time at which the phase is the tag is being read. It also throws the RSSI, which we said is not so useful for any localization purpose, and this distance is essentially the antenna location from where the reading was made. So, this is essentially what you would get from basically from a tag, and somehow you have to infer the you have to do the construct the hyperbola equations using this phase information and ultimately arrive at the final location of the tag. After reading the phases from each antenna position, you will get multiple hyperbola intersecting hyperbolas, and so you can see, take this A4, this is essentially the right side of the rack, the last tag on the right side, and you will see many intersecting points. All right. Now, how do you make out anything from this, where exactly is the tag? So, what do? You essentially apply a clustering algorithm, and we described that a good clustering algorithm indeed is the DB scan algorithm, right. So, this after applying DB scan clustering algorithm, many of these intersecting points are clustered and you arrive at some location which is one x and one y location, right. And you can see the results here. A2 if you take is minus 60 80, you ended up with minus 68 80, and A4 is 120 80, we ended up with 106 80. So, it is not so bad, right. So, so we have actually shown that you could use phase difference based spatial domain based phase difference of arrival and actually localize RFID tags.